December 12, 1944. 0620 hours. East bank of the Meuse River, Belgium. Hauptmann Friedrich Schneider commanded a German rearguard company that had successfully withdrawn across the Meuse River ahead of advancing British forces. His orders had been straightforward: delay British advance, fall back across the river, destroy the bridge to prevent pursuit. His engineers had executed demolition perfectly. The bridge was now a jumble of twisted steel and broken concrete lying in the river, creating obstacle that should delay British forces for days while they brought up bridging equipment and constructed replacement crossing. Schneider positioned observation posts on high ground east of the river where they could monitor British approach. His men were exhausted from 3 days of continuous fighting and withdrawal, but morale was reasonable given circumstances. The blown bridge represented breathing space, opportunity to rest, while British forces dealt with the river obstacle. Standard doctrine suggested British would need minimum 48 hours to establish crossing. Time to deploy engineers, survey the site, bring up bridging materials, construct new bridge capable of supporting armor. Schneider's force could rest, reorganize, and prepare defensive positions to contest the eventual British crossing. Dawn broke cold and misty. Schneider's forward observer radioed a report that made no sense. "Sir, there's a bridge across the river. British vehicles are crossing now." Schneider assumed his observer was confused, perhaps seeing wreckage of the destroyed bridge through morning mist. "Negative. Bridge was destroyed yesterday. Confirm what you're observing." "Sir, I'm observing a complete bridge. Steel construction, spanning the entire river. British trucks and armor are crossing in column. The bridge appears fully operational." Schneider moved to observation post himself, certain he would find his observer had misidentified something. Instead, he saw exactly what had been reported: a complete bridge spanning the Meuse, British vehicles crossing steadily, the structure showing no signs of hasty construction or weakness. The bridge looked permanent, solid, professional, as though it had always existed and the German demolition had been hallucination. Schneider's hands shook as he lowered his binoculars. His engineers had destroyed the bridge 36 hours earlier. British forces couldn't have constructed replacement bridge in that time. It was physically impossible, given the equipment and time requirements for military bridge construction. Yet the evidence was undeniable. British armor was crossing the Meuse on a bridge that shouldn't exist. Schneider's report to division headquarters was received with skepticism that transformed into alarm as other units reported similar observations. British bridges were appearing across rivers throughout the sector, constructed with speed that violated everything German engineers understood about bridge-building timelines. The Meuse River, which was supposed to provide days of security, had been crossed in hours. German defensive strategy predicated on rivers as obstacles was collapsing because British engineers could build bridges faster than German forces could retreat. The bridge Schneider observed was a Bailey Bridge, a British military engineering innovation that would prove more strategically significant than many weapon systems that received far more attention. The bridge had been constructed by Royal Engineers in approximately 8 hours using prefabricated steel panels, simple hand tools, and manual labor. No heavy machinery, no complex construction equipment, no weeks of careful engineering work, just trained soldiers assembling modular components with practiced efficiency. The quiet civil servants' revolution. The Bailey Bridge originated not from military requirements or high-level strategic planning, but from a British civil engineer named Donald Bailey, who recognized that existing military bridging solutions were inadequate for modern mobile warfare. Bailey worked at the Military Engineering Experimental Establishment and spent his spare time developing bridge designs using a Meccano construction toy set to test structural concepts. His insight was elegantly simple. Instead of designing custom bridges for each crossing, create standardized modular panels that could be assembled in various configurations to span different distances and carry different loads. Every panel would be identical, manufactured to exact specifications, with simple pin connections that required no welding, riveting, or specialized tools. The panels would be light enough for 6 men to carry, but strong enough that multiple panels assembled together could support 60-ton loads. The design's genius was its scalability. A short bridge over narrow stream might use single panel width and single panel height. A longer span over wider river could use double or triple panel widths and heights, with each additional layer of panels increasing the bridge's strength proportionally. The same basic components could create bridges 10 feet long or 200 feet long, capable of carrying jeeps or heavy tanks simply by varying how panels were assembled. Bailey submitted his design to military authorities in 1940. Initial reception was lukewarm. The design looked crude compared to sophisticated engineering solutions that peacetime military favored. But Winston Churchill personally championed the concept after seeing demonstrations, recognizing that mobile warfare required engineering solutions that prioritized speed and flexibility over elegance. Churchill later wrote that Bailey Bridge was among Britain's 3 most important technological contributions to winning the war, alongside radar and the jet engine. Production began in 1941, and by 1944, British forces possessed thousands of Bailey panels stockpiled in forward depots, ready for deployment wherever river crossings were required. The simplicity of manufacture meant British industry could produce panels rapidly without diverting capacity from more sophisticated weapons. The panels were shipped to combat theaters in standard cargo loads, stored compactly, and issued to Royal Engineer units trained in rapid bridge assembly. The assembly process. Bailey Bridge construction was fundamentally different from traditional military bridging. Conventional bridges required surveying, foundation preparation, heavy equipment for lifting structural members, welding or riveting connections, and days or weeks of construction time. Bailey bridges required none of this, just flat ground on the near bank where panels could be assembled, then simple pushing or rolling to extend the bridge across the gap. The construction process began with reconnaissance. Engineers would survey the river, measuring width, checking bank stability, identifying suitable approach routes for vehicles that would use the completed bridge. This reconnaissance took perhaps 30 minutes for experienced teams. The survey determined how many panels would be required and what configuration would provide necessary strength for anticipated loads. Next, panels were transported from storage to the bridge site and organized for assembly. Each panel was 10 feet long, 5 feet high, and weighed approximately 600 pounds, manageable for 6-man carrying team, but requiring coordination and physical effort. The panels were laid out in order of assembly, with pins, bracing members, and decking material positioned for easy access. Assembly proceeded in logical sequence. The first bay, consisting of vertical panels connected by horizontal bracing, was erected on the near bank. Additional bays were assembled behind it, each connected to the previous bay through simple pin connections that required only hammers to secure. As the bridge extended, it was supported on temporary trestles or rollers that allowed it to be pushed forward across the gap. Teams worked in continuous shifts, one group assembling new bays while another pushed the growing structure forward. The bridge advanced across the river like enormous steel caterpillar, growing incrementally as new sections were added at the rear, and the entire structure slid forward toward the far bank. The process was mechanical, repetitive, and could continue as long as supplies and manpower remained available. Well-trained teams achieved assembly rates of approximately one bay every 15 to 20 minutes, meaning a 150-foot bridge required roughly 2 hours of construction time once assembly began. When the bridge reached the far bank, final positioning occurred. The structure was settled onto prepared abutments, approach ramps were constructed, decking was completed, and the bridge was tested before being opened to traffic. The entire process, from beginning reconnaissance to first vehicle crossing, typically required 6 to 12 hours, depending on span length, terrain conditions, and whether construction occurred under enemy fire. The German intelligence failure. German military intelligence was aware that British forces possessed portable bridging equipment but consistently underestimated its capabilities and the speed with which it could be deployed. Intelligence reports described Bailey bridges as temporary tactical bridges suitable for light vehicles, and estimated construction times of 24 to 48 hours for typical river crossings. This assessment was catastrophically wrong. Bailey bridges could support 60-ton loads, heavier than any British tank in service. Construction times were measured in hours, not days. The bridges weren't temporary expedients, but robust structures that could remain operational for extended periods if necessary. Every assumption German commanders made about river obstacles providing time for defensive preparation was based on intelligence that bore no resemblance to reality. The failure stemmed partly from conceptual limitations. German engineers built excellent bridges, but required substantial time and equipment to do so. The idea that bridges could be assembled manually in hours without heavy machinery seemed implausible. German doctrine assumed bridge construction was engineering problem requiring sophisticated solutions, not manual labor problem that could be solved through prefabrication and trained work crews. German forces also underestimated British engineering capabilities generally. The Royal Engineers were highly trained, well-equipped, and experienced in rapid bridge construction through extensive training and combat operations in North Africa and Italy. German intelligence recognized that British engineering was competent, but failed to appreciate that competence had translated into operational capability that fundamentally changed how river obstacles affected military operations. The consequences of this intelligence failure were severe. German defensive planning throughout 1944 and 1945 relied on rivers providing substantial delays to Allied advances. Commanders positioned forces assuming they would have days to prepare defenses while Allies dealt with river crossings. Instead, British forces crossed rivers in hours, appearing on the far bank before German forces had completed withdrawal. The tempo of operations accelerated beyond what German doctrine could handle, creating cascading failures as defensive lines collapsed faster than new ones could be established. The Italian proving ground. The Italian campaign provided extensive opportunities for Bailey Bridge employment across terrain that should have favored defenders. Italy's geography, mountainous with numerous rivers running perpendicular to the Allied advance, created natural defensive positions that German forces exploited thoroughly. Every river was a potential stop line, every bridge a target for demolition. German strategy assumed this geography would slow Allied advances to grinding crawl as engineers struggled with continuous bridging requirements. The Sangro River crossing in November 1943 demonstrated Bailey Bridge capabilities dramatically. German forces had demolished all bridges and withdrew to to defensive positions on the far bank, confident that the river would delay British advance for substantial period. British Royal Engineers began bridging operations immediately, constructing multiple Bailey bridges simultaneously at different crossing points. Within 72 hours, 24 Bailey bridges were operational, allowing British armour and supplies to cross in sufficient strength to overwhelm German defences. German commanders were stunned by the speed and scale of bridging operations. Intelligence reports noted, enemy bridging capability exceeds previous estimates significantly. Multiple bridges constructed simultaneously suggest substantial stockpiles of bridging materials and trained engineering personnel. Recommend reassessing value of river lines as defensive obstacles given enemies' demonstrated ability to establish crossings rapidly. The Gothic Line operations in autumn 1944 extended Bailey Bridge employment to mountain warfare, where conventional bridging seemed impossible. Engineers constructed bridges across ravines, up mountain roads, and over rivers swollen by autumn rains. The bridges were carried forward in pieces by trucks and often by hand when roads were impassable to vehicles. Construction proceeded under German artillery fire, with engineer casualties accepted as necessary cost of maintaining advance momentum. One bridge became legendary among Royal Engineers, a structure spanning a mountain ravine where German demolitions had destroyed the original crossing. Engineers carried panels up mountain trails, assembled the bridge under fire, and completed construction in 18 hours, despite terrain that should have made bridging impossible. German observers reported the bridge's existence to headquarters with visible frustration. Enemy has constructed bridge across ravine, at location we considered impassable to vehicles. Bridge appears capable of supporting armor despite terrain. Recommend accepting that normal assumptions about terrain obstacles do not apply to British engineering capabilities. The Northwest Europe Campaign. The liberation of France and Belgium in 1944 created continuous bridging requirements as British forces advanced through terrain heavily defended by German forces who demolished every bridge during withdrawal. The Bailey Bridge system proved essential to maintaining operational tempo that prevented German forces from establishing stable defensive lines. The Seine River crossing in August 1944 saw multiple Bailey bridges constructed under German artillery fire as British forces pursued retreating German armies. Engineers worked in shifts, maintaining construction during daylight despite casualties from German fire. The bridges were completed within 48 hours of British forces reaching the river, allowing armor to cross immediately and continue pursuit. German forces that had assumed the Seine would provide several days' respite found British tanks appearing on the east bank before defensive positions were fully prepared. The Meuse crossing, where Schneider's observation post watched British armor crossing, was typical of hundreds of similar operations. German engineers demolished bridges competently, creating obstacles that should have required days to overcome. British engineers arrived, surveyed the crossing, brought up Bailey panels, and constructed replacement bridges before German forces completed their withdrawal to next defensive position. The cumulative effect was German retreat accelerating beyond sustainable pace as each defensive line was outflanked before it could be fully occupied. Market Garden operations in September 1944 demonstrated Bailey Bridge capabilities under most demanding conditions. The operation required rapid advance along single main road with multiple river and canal crossings. German forces defended each crossing and demolished bridges when forced to withdraw. British engineers followed advancing armor with bridge columns, constructing Bailey bridges at every demolished crossing. The bridges were completed rapidly enough that armor delays were measured in hours rather than days, maintaining attack momentum despite German defensive efforts. The Rhine crossing in March 1945 represented Bailey Bridge employment at maximum scale. British forces constructed multiple bridges across the Rhine, Europe's most significant river obstacle, using Bailey panels assembled into massive multi-span structures. The bridges were built under enemy fire, suffered casualties and damage during construction, and were completed rapidly enough to support the massive logistical requirements of armies advancing into Germany. German defenders could destroy the bridges through artillery or air attack, but British engineers would repair damage or construct replacement bridges faster than German forces could maintain sustained interdiction. The strategic impact. Bailey Bridges' strategic significance extended beyond tactical convenience of having portable bridges available. The bridges fundamentally altered how river obstacles affected military operations, shifting the balance decisively toward attackers who could cross rivers rapidly rather than defenders who relied on rivers as barriers. German defensive strategy in Western Europe during 1944-1945 relied heavily on river lines, providing time to re-establish defensive positions after withdrawals. The strategy assumed that rivers would delay Allied advances by days, allowing German forces to withdraw in controlled fashion, prepare new defensive positions, and potentially counterattack against extended Allied supply lines. Bailey Bridges eliminated these delays, allowing British forces to maintain contact with withdrawing German forces and prevent establishment of stable defensive lines. The cumulative effect was German forces conducting fighting withdrawal across entire northwestern Europe without achieving the pauses necessary for effective defense. Each river line that should have provided days of security provided only hours. German forces reached new defensive positions, exhausted from continuous movement and combat, lacking time to prepare fortifications, with British forces appearing before defenses were complete. The operational tempo exceeded German forces' ability to respond, creating cascading failures that accelerated Germany's defeat. The bridges also enabled logistics that sustained Allied advance. Military operations require enormous supply flows: ammunition, fuel, food, replacement equipment, medical supplies. These supplies must cross the same rivers that combat forces cross, and sustained operations require robust bridges capable of handling continuous heavy traffic. Bailey Bridges provided this capacity, supporting logistics that kept Allied forces advancing despite the natural obstacles that German geography presented. The final assessment. Friedrich Schneider survived the war and was interviewed in 1968 about his experiences during the German retreat through Belgium. When asked about most significant Allied capability that affected German defensive operations, his response was immediate. British bridges. We would destroy crossings, fall back, prepare new defensive positions, and before we'd completed preparations, British armor would appear. Having crossed rivers, we'd just demolish bridges over. The speed was incomprehensible. We couldn't retreat faster than they could bridge. The Germans couldn't believe how fast Britain built bridges across every river in Europe because the speed violated their assumptions about what was possible. They thought bridges required time, heavy equipment, and sophisticated engineering. British proved that bridges required prefabrication, training, and willing acceptance that manual labor could accomplish in hours what machinery accomplished in days. The result was German forces retreating across continent while watching British bridges appear behind them faster than they could destroy the crossings ahead of them. The strategic lesson was clear. Defensive obstacles only work if attackers lack means to overcome them rapidly. Rivers are excellent obstacles if crossing requires days. They're minor inconveniences if crossing requires hours. Bailey bridges transformed rivers from barriers into speed bumps, eliminating advantages that Germany's defensive strategy depended upon and contributing substantially to the tempo of operations that prevented Germany from establishing stable defensive lines during 1944-1945. The quiet civil engineer, with his Meccano toy bridges, had created weapon as strategically significant as many that received far more attention and resources. His contribution was elegantly simple solution to problem that seemed complex, proving that engineering excellence sometimes meant finding adequate solutions that could be implemented rapidly rather than perfect solutions that required extensive development and deployment times. The Bailey Bridge was adequate, simple, and fast, and in warfare, those characteristics proved more valuable than perfection.